We have already had one session on Tarot for a paper which is related to AI, which is Attention is All You Need. My preference of the paper that I wanted to discuss was more related to something foundational, and that's the reason why I chose this paper. I also have a physical copy of paper with me, so you might see me like going into it because I have some notes here while I'm talking. Um, so yeah, let's get started. The name of the paper is Simple Testing Can Prevent Most Critical Failures. It is an analysis of a lot of production failures in in some distributed data systems. We will go into details of which systems and what kind of analysis has been done in the paper. So to start, the idea is that real world outages are very real. So it is not a rare thing to happen. We know that real world distributed systems do experience outages. It has been seen in the I think recently also, I think 2 years ago, or maybe 1.5 years ago, there was an outage on Instagram, on Facebook. There have been a lot of outages in AWS in 2001. I'm just reading the examples from the paper. The paper is actually from 2014. That is why the examples here are a little bit older. But yeah, the reasons still are relevant why these outages were happening. So yeah, even when these systems are designed to be highly available, developed using good software engineering practices, and these are intensely tested, these systems still experience failures. So in this paper, the authors studied 198 randomly sampled user-reported failures. So when they say user-reported, they mean they did not analyze any of the failures which were kind of reported or discovered by the developers themselves. They were reported by the users, kind of saying that they had more of an impact because it was reported by a user. And the failures that were studied were on these systems: Cassandra, HBase, Hadoop Distributed File System, Hadoop MapReduce, and Redis. Um, and these systems were analyzed, and the failures in these systems were analyzed to get the answer for this question, that why do systems still experience failure? So the key observation of this research paper is that error manifestation sequences, they are relatively complex. When they say error manifestation sequences, what essentially they mean is the steps that happen uh, from the point where something went wrong to the failure. It's not simple. It is a mix of complex things happening one after the other. And the paper also discusses that a lot of different sections of this story have been researched on. So, for example, root causes categorization. So, what are the root causes of these failures? That has been studied before. Different types of causes, including misconfigurations and bugs and hardware faults and system failures, they have been studied in isolation. But the aim of this paper was to know the whole story. So, yeah, it was observed that it requires an unusual sequence of multiple events with specific input parameters from a large space to lead the system to fail. So, a mix of very particular things happening in a particular order, sometimes like in a large input state, was needed for these events to happen. So, yeah, the thing is that these systems on which these outages or failures were happening are the systems which are actually very much covered by unit tests. Error injection is done. Bugs like, sorry, bug finding tools like find bugs, etc., have been deployed widely in these specific organizations. In these specific systems where this test was done, but still failures were observed. So this proves that methods like error injection, unit testing, it's not enough. And when the term unit testing is used, it means top-down approach. So when we say top-down approach of testing, which means we are starting from the top and thinking, oh, this is my feature, let's say, and what could go wrong, and then kind of imagining, instead of going from bottom and figuring out, okay, this here is the error block. What could happen? What kind of different errors could happen, and then kind of building up that how can this error be thrown by this method or this feature. So yeah, so one of the key observations was, I mean, in some parts of the slide you will see like numbers which is somewhat like this. So almost all, like 92% of catastrophic system failures are a result of incorrect handling of non-fatal errors explicitly signaled in software. So when we use the term catastrophic failures in this context, the authors say that catastrophic failure is the failure that affects all or majority of users instead of a subset of users. So, as I mentioned earlier, almost all, which is 92% of the catastrophic failures, are a result of handling of non-fatal errors explicitly signaled in the software. So to simplify it, it basically means that error handling code is often the reason of these failures. Um, they have more statistics around it. So 35% of these catastrophic failures fall into these three trivial patterns. And actually, when I was reading this paper, even I felt that it sounds so stupid, because if you read different parts of it, the first one is when the error handler is simply empty or contains only log printing statement. So, okay, you throw an error while you're catching it, you don't do anything after you catch the error. Or sometimes you just exit exit the function or the system call, and that is also something that leads to a bigger problem. So which is the second point, which is the error handler aborts the cluster on an overly general exception. And the third one is the error handler contains expressions like fix me or to do in the comments. So 35% of catastrophic failures, which is not a small number, was because of these three things, which is something, these kind of things can be easily tested, but they were not, and that's why they led to these failures. So um, in the paper they also discussed that based on these trivial patterns they built a tool to test these kind of patterns in a given system. They also ran this tool which they call aspirator. We can discuss about that later in the paper. And they were able to find more similar kind of bugs, which are so trivial, but they can lead to these catastrophic failures. Now, the next part is about 74% of the failures are deterministic. In that, they are guaranteed to manifest with an appropriate input sequence. So the idea is, out of all the failures that they discovered, 74% of them were deterministic. The word deterministic here means given um, a set of input events, they are guaranteed to happen if these input events happen in a certain order. Then almost all failures are guaranteed to manifest on no more than 3 nodes. So right now we're just going through like the key observation. We will go through each of these things in a bit more detail later on. So yeah, 74, almost all failures are guaranteed to manifest on no more than 3 nodes. So if we were to reproduce these failures, you do not need more than 3 nodes. And I think when they say almost all, I remember it was around 90 something percentage. I'm not able to find it right now, but it was around 90 plus percentage where you do not need more than 3 nodes to reproduce that particular failure. And then 77% of these tests can be reproduced by a unit test. Sorry, these failures can be reproduced by a unit test, which sounds really surprising, but it is the of observation of the authors of the paper. One thing also about the data set that the authors were using, the systems and the specific errors and the failures they studied, they tried to choose systems which had a lot of representation, like diverse type. Although these systems were data intensive programs that included data storage and analytical systems. They included both persistent stores and volatile caching. both written in Java and C, both master slave and peer-to-peer design. So like HBase, HDFS, Hadoop, MapReduce, and Redis, these use master slave design, while Cassandra uses a peer-to-peer gossiping protocol. So yeah, so they were trying to be diverse in the kind of systems that they're studying. Again, the representation of selected failures, the failures that they selected were mostly software failures and not hardware failures. Um, and yeah, obviously there are possible observer errors in their study. Now let's move to the next part, which is uh, right now, until now, we discussed, okay, what happens, what leads to this error, what are the few key numbers which lead to these critical failures and all those things. So now let's see what is the complexity of the failures. When I say complexity of the failures, as I mentioned earlier, the manifestation of the failures is complex. So one thing, the majority of the failures require more than one input event to manifest, but most require no more than three. So if you see this image, this table on the left side of the screen, so they basically categorized different input events, and then the percentage next to them is the percentage of failure where this input event is required to happen. So I think, yeah, I cut the description of this table by mistake, but it says input events that led to failures. The percentage column represents the percentage of failure where the input event is required to trigger the event. Most of the failures require multiple events, so the sum of the percentage is greater than 100. So if you see, most of these events require most of these failures, which is 58%, require starting of a service. Then the next one is it requires a file or a database write for a client. The next is unreachable nodes, and then so on and so forth. So these are the input events that need to be happening in some order for the failure to happen. And again, 77% of the failures do not require more than one input to manifest, but 90% require no more than three. So only three can be present and the issue will happen. The failure can be reproduced. So now the second part of this is the specific order in which the event is happening is also important. So let's just pick up any three of these randomly. Let's say node restart, configuration change, and unreachable node. Um, in 88% of the cases, the order in which this is happening is also important. So there is a picture here which I uploaded, which is an example of a failure that happened. So this is an HDFS failure where a data block remains under-replicated, potentially leading to a data loss. Here, three input events are needed, and these are shown in the box. So the input events here are upload BIKA 100, append, and then start DN2. DN2 is data node 2, and append to BLK is, yeah, just another of write for the client. You can, sorry, the first one is a write from a client. The second one is append, again it's a write, and the third one is start a new node. So you can see here that what's happening, how the data is being lost. So the first thing is the user uploads a data block, causing HDFS to assign a general stamp. So in step, sorry, yeah, here the user uploads some data block and an ID kind of thing is assigned to it. So 100 is the generation stamp. When this thing goes to the name node, and it goes to the data node, and it is added to something called a replication queue, uh, causing HDFS to assign a generation stamp. Name node asks data node 1, which is DN1, to store this block. And because this block is currently under replicated, it adds it to need replication queue. In the second step, the user appends to this block. So this is the second step here. The user appends to this block, causing data node 1 to increment the stamp from 0 to from 100 to 101. So what is happening is the updation of the generation stamp number, whatever, is happening from 100 to 101. However, this is not done on the queue. Now, what happens is, because this is not done in the queue, this is being updated when another data node starts. So the name node asks data. So the name node asks data node 1 to replicate the block to data node 2, but because the generation stamp from the queue does not match, it keeps on refusing to replicate. So here, basically, the order in which things are happening is important. If the start of the data to node would have been done before the append, maybe things would have been different. So this is one of the findings, that the order matters, and this is an example of where the order is mattering. Now, because when we see that this is like a list of events which was leading to this behavior, we can also look at them as opportunities for improved testing, which is the point of the whole paper. So if you see this table again, the most important, sorry, the one that is being the one that has the most percentage is starting a service. That means that more than half of the failures require the start of some service. And it also suggests that uh, starting of a service obviously needs to be uh, tested more. So about more than half more than half of the failures required the start of some services. About a quarter of the failures triggered by starting a service occurred on systems that have been running for a long time. So, the thing is, let's say some system is running, and for doing something, a service starts up. And this starting of a service is a point which could lead to a failure in the future, because something wrong went while starting of the service. So the starting of the service should be tested. Although they saw that for more than about a quarter of the failures triggered, sorry, they saw that, yeah, for a quarter of these failures, you want to have a system that have been running for quite a long time. Even though this might be difficult to reproduce, because you want the system to be running for a long time, it can still be done by intentionally forcing to start the service during the testing. I mean, it will not cover all of it, but doesn't mean that you don't test the start of the service at all, because yeah, it is responsible for 58% of the errors that are seen by this observed by the authors of the paper. The second most, just going back to the picture again, the second one is I mean, file database and write is something, but it is something that has not been actually discussed. I think that is because depending on how can you actually test that. So that has not been discussed, but the next one that is being discussed is unreachable node. So the presence of unreachable node and it being like 24% here is actually quite surprising. And the reason for that is that because we are working with systems that are distributed, it is very much expected for individual nodes to crash, and this happening regularly, like in large data centers. But still, this is a reason of a lot of failures, which means that the tools that are capable of injecting network errors while these tests are done should be used more extensively while inputting other events during testing. So the unreachable node case should be tested more. And same for the adding node and the configuration change. Configuration change is not too different from unreachable node. It's 24 and 23. And then the next one is 15. So the same thing applies to adding a node and configuration. configuration changes. So if I can quote from the paper, um, 23% of the failures are caused by configuration changes as per the table. And out of those, 30% involve misconfigurations. The remaining majority involve valid changes to enable certain features that may be rarely used. So the tools should be extended to combine both valid and invalid configuration changes. Again, the next part is about adding a node. So which is around 15%. So 15% of the failures observed by the authors were when a new node was added to a running system. Also, this also is somewhat alarming given elastically adding and removing nodes is one of the principles of cloud computing. It suggests that adding nodes to be tested, it suggests that adding nodes needs to be tested under more scenarios. Also, uh, the production failures that were studied during this paper typically manifested themselves on configurations with large number of nodes, and that raises a question of how many nodes are required for an um, effective testing and debugging system, which we actually did uh, which we actually did read earlier and is also mentioned in the paper again, is that you do not require more than 3 nodes. 98% of the failures are guaranteed to manifest no more on no more than 3 nodes, and 84% will manifest on no more than 2 nodes. So this also implies that you do not need to have a large cluster to test and reproduce failures. You can test only in 3 nodes, uh, but obviously there will be some cases that might be left, but you are going to according to probability, you are going to cover a lot of the cases out of the total ones, given that 98% are guaranteed to manifest. Yeah. Um, the next thing is about the role of timing. When I say the role of timing, I mean what is the role of timing in all these input events which were mentioned um, on this screen? How is timing important? Is it important or not? So again, the key question for testing and diagnosis is whether failures are deterministic or not. So, deterministic means whether they are guaranteed to manifest if the required sequence of input events occur, and non-deterministic means it is not guaranteed that they would happen if you do the same steps one after the other. So, they figured that 74% of the failures were deterministic and the rest were non-deterministic. Also, it is easy to test the failures that are deterministic, because once you know what are the input events uh, that are causing the failure, you can just reproduce it, and if you can reproduce it, it is easier to test them. And also, the failures can still be reproduced after inserting additional logs, embracing traces, or using debuggers. The next observation about timing was among 51 non-deterministic failures, 53% have timing constraint only on input events. So how is this important? The idea is, okay, now 51 out of these non-deterministic failure, almost more than half of them, 53%, you need the input events, and only the timing for these input event matter to reproduce um, the failure. In other cases, other than these 53%, the timings of the events that are induced due to these input events are also play a role. Let's see this picture on this table on the left side. So the first one tells you the breakdown of the number of failures that are deterministic. So in Cassandra, it was 76%, which was 31 out of 41. HBase, it was 71, HDFS 76, and it was the maximum in Redis, which was 79. And for non-deterministic, these are the different breakdowns. So the timing between input event and internal executed event is 53%. Multi-thread atomicity violation was 25. Multi-thread deadlock was 6%. Multi-thread lock contention was 8%, and other 8%. So if we talk about the 53% where the time constraints are only on the input events, in that case, you can say that this can be tested and the timing can be actually controlled by a tester. So yeah, I wanted to move to this diagram here, which shows what happens in a non-deterministic failure and how timing is important. So what happens is, first, uh, the order of events are in the box. So this is a region server, an error happens, and this is the H master. So when the error happens, the master thinks that it cannot connect, and because it cannot connect, it assumes that the region server is dead. Now it recovers rs dash region server, some other region server region data from its hlog, and finishes the recovery, and a new region server is now assigned to that recovered region. Now, while this was happening, the region server is just had there was just a network error. It was not dead, and now it's back. When it's back, it loads its hlog. Hlog meaning its write ahead log. So, which means while there was a network error, um, there is a write ahead log where everything that happened is appended, so that if there's a network error or the machine itself, the node itself is down, you can see what all happened during that and reproduce it and rerun it in a way which is in the write ahead log. So the write ahead log is rolled. Now it receives new client writes. It received new client write which are written here, but since there is another region uh, rs dash, so like a new region server, the client write that is written here is lost. Now what's the importance of timing here? The timing importance is, if the input operation and the external state internal external sorry internal execution state here is the dependency. So if the order of these were swapped, probably not probably if the order of these were swapped, then the failure would not have happened. There would be no data loss. That is what I'm trying to say. So yeah, in case of, so this thing actually can be test by a unit test by having a timer. You can test them easily, but it is difficult to reproduce the failures other than this, where multi-thread atomicity violation is there. So anything that is related to more than one thread will be difficult to test. Also, again, same thing. If there is shared memory, multi-threading, interleaving, it will be difficult to reproduce this. Which again brings me to the next section, which is about log-enabled diagnosis. This means the idea here is that overall, the authors found that the logs that were output by these systems were very rich and had a lot of useful information. And also they're assuming that the default logging verbosity was used. They were not logging any more than usual or less than usual. So yeah, a default verbosity level was used, and still it was very much rich in information. And the finding was that 76% of the failures printed explicit failure related errors. So also, this somewhat contradicts with the finding of one more study done by the previous study done by the same authors on non-distributed systems, where only 43% of the times the explicit failure related messages were logged. So comparing the distributed systems versus the systems which are non-distributed. In the case of non-distributed systems, the number was 43%, while for distributed systems, you could see explicit failure-related errors 76% of the time. And the the conclusion of the authors is that there are three possible reasons for that happening. The first reason is that since distributed systems are more complex, they're harder to debug, developers likely pay more attention to logging. The second one is the horizontal scalability of these systems make the performance overhead of outputting log message less critical. So because you can have horizontal scaling. You can output more because, you can output more log messages because it will be less critical for you. And the third is communicating through message passing providers. Obviously, if there are multiple nodes in the system, it is a distributed system, you want to you will be communicating through message passing in between these nodes. um, for example, if two nodes cannot communicate with each other because of the network problem, both have the opportunity to log the error. And this is the reason why there is a lot of logs that are found in this case. The second observation was that for 84% of the failures, all of their triggering events are logged. So the difference between the first and the second one is, in the first one, explicit failure related error messages are being logged, while in the second one, all the events that are triggering the failure are being logged. Now, because everything is logged, not everything, but yeah, in 84% of the cases, everything is logged, it can be replayed but it would be nicer if tracing is also enabled in these, so that it is easier to reproduce and see what's happening. But another finding was that because there is so much logging in general, that logs become really noisy. So the median number of log messages printed by each failure was 824, and this 824 number is when they reproduced the failures that they're talking about. So it was not in the actual system, it was in their system with in their reproduced version of those systems, which had minimal workload because it was just a reproduction. So this is still a very big number. So the problem or the issue or the thing that needs to be improved here is to have uh, more and more refined logging, or a way to have a trace ID or something like that. So also one more thing was that everything is logged at info level, so you can't really filter out of that, and it becomes very difficult. Although the failures have the logs have a lot of information related to the failures, it is very difficult to actually find it. So this is an opportunity to make the logs better, more traceable. That can be done. Again, I mean, I have been using the term reproducibility quite often in the past few minutes. So again, this section is all about reproducing the errors. So the finding was that it seems that the issue is hard to reproduce, but that is actually not the case. And the reason why it seems that it is hard to reproduce is that conventionally you think that the failures that occurs on these large distributed systems are extremely hard to reproduce, and they require users input. The user's input may or may not be available due to privacy concerns. We might also think that it is dependent a lot on environment. I think someone is not on mute. Can you please mute yourself? Thank you. Um, so I think I need to check. Okay. Yeah, coming back to the failure reproducibility. So it seems that you might need users' data, which might or might not be available. Maybe you have to set up an environment that mirrors the one in production. Cost of third-party libraries and all these things are often the reasons that are cited, um, that as to why it is difficult for the vendors to reproduce the production failures. But the findings of these studies say that majority of these failures can be reproduced by a unit test, and the reason is because they're deterministic or they can be controlled by timing, as discussed earlier. And again, the same thing, contrary to popular belief, it can be done irrespective of the user data, and only the input sequence that we actually discussed in some slides ago is the thing that is required. So there is an example of a unit test for testing a failure. Um, Let me just uh, figure two. Yeah, so it is actually writing a unit test for testing this failure. So here the essence is the timing. So if you see, it starts a mini cluster which has one master and two region servers. Then it simulates h log splitting when RS cannot be reached. Then it simulates the region server's log event. Now a lot of writes happening uh, to the R dash region, and then the assignment of a new, and then you check if any rights are lost. So it is essentially just mirroring the whole thing that happened on production on the failure during the failure, and it can be reproduced and checked if we are actually losing any rights or not. And for 77% of the cases, this can be done. This can be done, and the testing can be done just with the unit test, and it depends only on the input events and their orders and sometimes timing, not on the production environment or on the user's data or anything of that sort. Um, also the failures actually that cannot be reproduced easily are the ones which depend on a particular execution environment or were caused by non-deterministic thread interleavings, but still they are not the majority. They are a minority in the total number of failures that were observed. So the last the section of the paper, which is actually quite interesting, is talking about catastrophic failures. Again, catastrophic failures is when all or majority of the users do not have normal access to their system. And in this paper, they specifically touched catastrophic failures because they are the ones with the largest business impact to the vendors. Also, it is surprising that such a huge percentage of failure is catastrophic, given that these systems are actually designed to exactly prevent these things. You don't want all of your system to come down, and that is exactly what is kept in mind while designing these systems. But the thing is that it still occurs. And interesting facts about it is that almost all, which is 92% of these events, are a result of incorrect handling of non-fatal errors, which are explicitly signaled. I think this was also mentioned in the beginning of the key observations. So it is one of the finding is that catastrophic um, errors happen due to initial non-fatal error, which is handled in a faulty way. And um, also, this prevalence of incorrect error handling is actually unique to catastrophic failures. In comparison, only 25% of non-catastrophic failures involve incorrect error handling. But in terms of catastrophic failures, 92% of the time it is because of non-fatal errors. Um, Also, um, catastrophic errors are the catastrophic failures are also because of not only because of poor error handling, but sometimes because of no error handling. So there is error handling which is empty. The things written inside the cache block is a to do or something like that. And sometimes it is also just wrong logic in place. So error handling is actually the most practical defense for all these catastrophic failures, because it is actually impractical to tame all the varied sources through which other kind of issues can come up. And this is actually one of the one of the main guards which you can use, and practical also, to basically prevent these errors from happening. Now, again, there's a whole section about trivial errors, that trivial mistakes that are in error handling, and which takes me to the second point mentioned here, which is 35% of these catastrophic failures are trivial mistakes in error handling, ones that simply violate best programming practices and that can be detected without any system specific knowledges. So, one of them is sometimes ignoring the errors and allowing them to propagate, which is a well known bad programming practice. But you will see that uh, this is still there in the code, and it is leading to many catastrophic failures. And sometimes the thing I think I mentioned earlier as well, the issue is that wrong exception is caught, and the developers are not explicit about what exception they want to actually use. I think I added a picture for this one. I think, um, I'll try to share the screen which has this picture because it is actually interesting. Um, I need to stop presenting and go to the other section. Yep. So this is the, I'll zoom in a little bit. I hope this screen is visible. This is the example that I was trying to talk about, where a wrong exception, if you see figure 8, there's a try block where something is done. And then these lines were added, the lines which have plus in front of them were added as a fix. But initially, it was catching a throwable error, which is, it is a wrong exception that is being caused, and it was exiting the system after that. So the developer wanted to exit the system only when this error called remote exception E was being thrown. But instead of catching that error, they caught this throwable T and made the system exit. And because of this, the entire cluster was brought down. Another example here is a data loss in HBase where error handling was simply empty instead of a logging statement. So this line was actually added later. Same here as in, mentioned. This is from MapReduce where there was just a to-do line. And here is the case when the error handling code was wrong and not nested at all. And the rare sequence of event, a rare sequence of event caused newly open to throw a rare keeper exception, which simply took down the whole system. So these are the three different kinds of errors. The paper also discusses about some system specific bugs. So the things that we talked about right now are not system specific. They are just, okay, don't leave the catch block empty, don't have like a to do there, don't catch the wrong exceptions, don't make the system exit on that, don't make the system exit, and don't catch exceptions which are so wide. But system specific bugs are the ones which are caused by incorrect error handling, um, where system specific knowledge is required to detect the bug. It was seen that in 23% of the catastrophic failures, while the mistaken error handling were system specific, they are still easily detectable. More formally, the incorrect error handling in these cases would have been would have been exposed by 100% statement coverage. So if the code inside the error handler is properly tested, it would be still helpful. And you would need to write test explicitly for all the parts of your error handling and all the section. If 100% code coverage would be there, still 23% of them are easily detectable. um, yeah, this seems, again, this seems difficult, but it can be done with bottom up approach, as I mentioned at the beginning of the session, which means you see what all different kind of errors are possible, and then for each of them try to work your way up. How could this be thrown by this? And then if this is thrown, how would that be handled in another part of the code where this function where I'm throwing this error, or this error is being thrown, sorry, being caught, um, changes the flow of the function or the method from where this one is being called. So yeah, that is one thing about this. I'll go back to um, sharing the right screen. Oh, yeah, here. Not sure if I'm able to. Okay, for some reason, I'm not able to share the specific tab, so I'll share my whole screen. Yeah. At the end of the paper, which we're approaching, they actually implemented a system called aspirator, where they actually basically checked for all these trivial things that we were talking about. If you're interested in reading more about the aspirator, you can read the paper. I'll actually also link the paper on the chat, and I'll stop sharing here. Yep. So this was the whole idea of the paper, which is that it might seem that there's a lot of different things happening, but when these specific distributed systems were being tested, a lot of things were seen as being more predictable. And because they were more predictable, um, different testing scenarios can be done. One interesting thing, actually, which I forgot to mention, was when they when they built their system called aspirator, based on the errors and their observations. They ran the system again on the existing, on Cassandra and all these things on which their study was developed. They found, I think, more errors. Um, I think, yeah, they found around 1,500 more errors, something like that. I can't find the number, but it was mentioned somewhere in the paper that they were able to find more errors in the same system, which was interesting. They also mentioned a little bit later in the um yeah, sorry, I found it. So they reported 171 bugs and 171, not 1,700, and bad practices to the developers through their official bug tracking website. To this date, 143 have already been confirmed or fixed, and 70 have been confirmed but not fixed. 17 were rejected, and others have not been received any responses. So if you want to read a little bit more about their experience with the developers, it's a good idea to read the end of the paper. Is there anything, like, if anybody wants to add to this from their experience, then this is a good time to speak up.